I might get started. Welcome everybody to Astronomy Education. My name's Colin Hill, and tonight I'll be talking about observing with a small telescope. So basically this is just a presentation on what to do when you're set up for an observing night, what equipment you need, looking at the various conditions, and what you can expect to see with a moderately sized telescope. Right, if I could advance the slide. All right, so what is a small telescope? So it's basically a typical amateur telescope, right? So the variables are aperture. So aperture, larger means brighter, with better resolution, and able to withstand greater magnification. So a small aperture, you might only be able to go up to about, say, 250 times. With a big aperture, you might be able to go up to like 400 times. But it also depends on other factors like the seeing. The quality, better, usually means a sharper image with little aberration across the field. So you won't get the, like with the cheap refractors, for instance, you often get chromatic aberration, like colour fringes around all the stars. Because they're cheap, they've only got a single lens in them, and a single lens doesn't focus all of the colours to the same focal point. And the mount. Now, the mount is probably one of the most important things of the whole setup. You need a solid mount because there's nothing worse than having a bit of a wind or you bump it and everything moves and that. So a nice solid mount is also important. So what do you need when you're setting up for a viewing night? Obviously, you need the telescope, or binoculars, or both. So it sort of depends on the type of objects you're trying to see for the night. If it's a wide field you're interested in, then binoculars are probably best. But having both gives you the flexibility. A selection of eyepieces and filters. Depending on the weather, a dew shield, in case it's very wet, the dew gets on everything, and the appropriate clothing. Obviously, if you've been up at Stockport in the middle of winter, it can get down to like freezing, and some people have actually had ice forming on their telescopes in the middle of winter there. And a red torch. So red light has a minimal effect on your night vision because your eyes are least sensitive to red light. So it doesn't affect your night vision if you're using a red light. If you use a white light, it can take you about half an hour for your eyes to recover after being exposed to white light. And obviously, it's useful to have a torch, a map reading, taking notes, and actually just generally finding stuff. And you may want star maps, a planisphere, or if you're a bit technical, you can have a laptop with some planetarium software on it. And an objective is also nice to have. It's not essential, but it's sometimes desirable to have an objective for the night. It might be the moon, the planets. You might just want to concentrate on double stars, messier objects, or objects all within a constellation. There's lots of resources for this. There's the bulletin itself, the ASA bulletin, has a lot of information on it, especially on comets. And the internet, obviously, is another great resource. One site that I've used quite often, it's called tonightsky.com. So this is a screenshot here of it, and it's quite good. You could put in your location, it can be anywhere on the planet, and then you put in the type of objects you're interested in. You put in the range of magnitudes and the what time you want to start viewing, what time you want to finish viewing. Yeah, you put all these parameters in there, and then it comes up with a list from brightest to faintest of all the objects that match your search criteria. And the other good thing about this site is that it remembers your settings. So if you go into it at another time, you don't have to put all those parameters back in again. And I used it quite a bit, not necessarily for viewing, but for astrophotography, which is quite good for that as well. So before you start, there are some things you need to consider. Is the weather with number one. Obviously, if it's cloudy, it's no point going out there. So there are some resources online, Skippy Sky and CFN, which stands for Cloud-Free Night. So those resources can give you an idea of what cloud cover you can expect to get on your viewing night. The other consideration is wind. So you might have a lovely clear night, but if it's a 30-kilometre-an-hour wind, it's not going to be very pleasant. Moon is also a very big consideration. If you're not observing the moon, then no moon is best. But if you are observing the moon, then less than first quarter is probably best, because this will enhance surface features like shadows along the terminator. So along the terminator, you can see there's a lot of detail, where on the illuminated side, it's all washed out. So when you're looking at a full moon, there's nothing worse than looking at a full moon in a telescope. There's just no shadow relief at all. And if the moon is out and you're looking at other objects, the moon can wash out the fainter objects. It doesn't really affect planetary viewing, but for deep sky stuff, you really don't want much moon in the sky, unless you've got some filters that can help. And the terrain as well. You've got to be aware of obstructions. Trees and buildings are obviously a problem. And also try to avoid being in the line of bright lights, street lights and that sort of thing. So polar alignment. So this is important if you've got an equatorial mount. It's not so critical for viewing as it is for astrophotography, but you do need to get it reasonably accurate, especially if you've got a go-to telescope. It relies on having the polar alignment accurate before you can start using the go-to features of your telescope. So what you have to do is you determine the latitude of your viewing site. So Adelaide is approximately 35 degrees south. So you set your polar axis of your mount to the same angle. So there's your polar axis here. So you set that angle there to the same angle as your viewing site. In this case, about 35 degrees. Then you've got to point the polar axis to the south celestial pole. There's a couple of ways you can do that. Some telescopes have a polar scope in them. So you look through them and you'll actually look at the pole. And the pole looks like something like that. In the southern hemisphere, there's no bright stars near the south celestial pole. So it's a little bit tricky trying to match this pattern of stars to try and get to this point here. As I said before, if you're just doing viewing and not astrophotography, it's not super critical. So you can sort of use this method here. If you find the Southern Cross, in this case it's upside down, and the pointers, Alpha and Beta Centauri. So if you take a perpendicular line between the pointers and out into space, and then the long axis of the cross, take that out into space, where those two imaginary lines intersect is roughly where the south celestial pole is. So if you're just doing viewing, that's probably good enough. And if you've got a permanent site like in your backyard, you can actually sort of paint some marks on the concrete, so you know where to put the tripod. Eyepieces is a bit of a minefield. So the magnification of a telescope is the ratio. See, that does get in the way, doesn't it? Yeah. It's a ratio of that should be focal under there. The ratio of the focal length of the telescope to the focal length of the eyepiece in use. So for example, if your telescope has 1,000 millimeter focal length and your eyepiece is 25 millimeter, you divide the eyepiece into the telescope focal length. So 1,000 divided by 25 equals 40. So 40 will be the magnification of your telescope. So you want to have a range of eyepieces that you can change to adjust the magnification depending on the type of object that you're viewing. Now, eyepieces, they can vary dramatically in price and quality. And they come in 3 different barrel sizes primarily. The 0.96 inch is typically what you would get in a Kmart telescope. The little bargain basement ones, they're usually not very good. The majority would be the 1.25 size, and they also come in 2 inch as well. There's also a 3 inch one as well. I've never seen a 3 inch, but that's more of a professional size, barrel size. And also consider getting a Barlow lens. A Barlow lens is a lens that you put between the eyepiece and the focuser, and it effectively doubles or even triples the magnification. So it means that you can, with one Barlow lens, you can reduce the number of other eyepieces you need, because by using different combinations, you can get different magnifications. And also a wide field eyepiece can be beneficial to enhance the visual experience by encompassing more of the sky, and you can see a lot more with your eye than a narrow eyepiece can. And filters. Oh, this is another can of worms. So filters are used to block or pass certain wavelengths to enhance the image. So we have LPR, which stands for light pollution reduction, and UHC, which stands for ultra high contrast. So these reduce sky glow caused by sodium and mercury vapor lamps to increase the contrast of faint objects. Unfortunately, nowadays, most of these street lights are going to LED, which are like wideband emission. So these filters are not so effective with LED lighting. But you can see here that what they do is they let these bands through, which are the hydrogen and oxygen emission lines from astronomical objects, but they won't pass like the lines coming from mercury vapor lamps and the sodium vapor lamps. Then we have neutral density filters. So if you are looking at the moon and it's quite bright, you can screw one of these in, and all it does is just reduces the basically all the wavelengths by the same amount. I remember once up at Stockport, I had a look at the moon through the 15 inch and it was about 3/4 full, and it was so bright, that's all I could see for the next half hour was this moon in front of my face. It sort of burnt into my retina. So it is helpful to reduce the glare. You can see here, this is like a before and after putting in the filter. Then we have some specialized filters, an O3, which is double ionized oxygen. O1 is actually neutral, so that's why O3 is double ionized. So this one just lets through the line for oxygen 3, basically. And this is useful for emission and planetary nebulae. Hydrogen alpha is up here. Hydrogen alpha line's up here. It's useful for looking at the sun, and they're very expensive. Hydrogen beta, useful for observing faint nebula like the Horsehead. And then you can get a range of color filters as well. and they can be useful for looking at the planets and trying to enhance features on planetary viewing. Okay, viewing. So at low light levels, your eyes do not perceive colour. So you've had a look at, say, the Orion Nebula, and it just looks grey. So at low light levels, your eyes will just see shades of grey, basically. Unless it's a bright object, like a planet. And sometimes people can see a little bit of colour in the Orion Nebula, perhaps a bit of green, but not much else. So you take your time on each object and try different filters and different eyepieces to try and get the best view. Very faint objects, like galaxies, sometimes trying averted vision will help, because your peripheral vision is actually more sensitive than when you're looking straight on. And so sometimes you can be looking at a galaxy in an eyepiece and you don't see anything. But you sort of look away slightly and then suddenly it pops up in your peripheral vision. And try and avoid objects that are within 20 degrees of the horizon, because the seeing is worse as you get closer to the horizon, because you're looking through more atmosphere. So especially if you're trying to look at planets, planets are very susceptible to the seeing conditions, because they're very small, and you have to use a lot of magnification on a planet, so they're much more susceptible to the seeing conditions. And on the planets and the moon, it's best to start off with low magnification first, and then crank up the magnification as the seeing permits. Because some of the times the planet may look reasonably good, but as you increase the magnification, they turn into a blurry mess. So just start off low first and then work your way up. So what can you expect to see? So you've all seen these lovely images that you get from the astrophotographers. And a lot of people, when they're looking through a telescope for the first time, this is what they expect to see when you look through the eyepiece. These lovely images full of colour and detail. But in reality, it sort of looks more like that. So once again, you lose all your colour, lose a lot of your detail. And like with galaxies, sometimes virtually all you can see is the core of the galaxy and not much else. All right, the planets. So Mercury and Venus, they're always close to the sun, relatively close to the sun, especially Mercury. So you really have to observe those soon after sunset. The Venus, though, it's one of the few objects you can actually have a look in the daytime. That image there, I took that in the middle of the day. The tricky part is finding it. But once you've found it, it's actually quite obvious in the sky as a little point of light, even with a naked eye. But you only have to take your eye off it for a second and then you can't find it again. But because it's such a bright object, the contrast is sometimes better in the daytime. It's not sort of so glary. Now Mars is a bit trickier because its orbit is beyond ours. We sort of have to catch up with it every 2 years. So we only get a window every 2 years to look at Mars, and that window lasts for perhaps a few months. So you can see as we approach opposition, the planet gets bigger, 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 and then as we go past opposition, it gets smaller and smaller and smaller again. So we just get this small window of a few months every 2 years where we can observe Mars. With the outer planets, we get quite a large window every year because they do move fairly slowly across the night sky night by night. So we get quite a few months of good viewing for the outer planets. So Jupiter, because it is such a large planet and it is the closest of the outer planets, it's always nice and big and bright, and you can usually see lots of detail on the surface or in the clouds if the seeing is good. So it's a bit hit and miss, but you can see detail like the cloud bands. You can see the great red spot, and sometimes you can see moon transits as well. So you can see the shadows of moons as they cross the planet. And then at low magnification, obviously you can actually see the 4 Galilean moons around the planet. Saturn's always a showcase item in the eyepiece. This year has been interesting because the rings of Saturn are actually edge on at the moment. This only happens about every 20 odd years or so. And I think earlier this year, they actually disappeared for a week or two. Unfortunately, it was very close to the sun at the time, so we missed that. But they're still very, very almost edge on at the moment. And over the next few years, they'll slowly open up and we'll be able to see them in their full glory. Uranus and Neptune, much more challenging. They're a lot further away and they're smaller. And they usually just look like blue-green small discs, usually with no detail on them at all. Comets are always an interesting object to observe. Not so much in a telescope though, because comets are actually quite large objects. The tail can spread many degrees across the sky. So binoculars are probably a better choice for comets than a telescope. Then we come to emission nebula. So we have our favourites here, the Lagoon, the Trifid, Eta Carina, the Tarantula, and of course Orion. This is approximately sort of what you would expect to see in an eyepiece on a good night. Probably not quite as much colour as I've shown there, but that's sort of what you'd expect to see from these sort of objects. And as I said, you can try different filters, try and enhance the image. Then we can come to planetary nebula, and SNR stands for supernova remnant. So the Crab is a supernova remnant, and it's fairly faint. Some planetary nebula are actually quite bright, but quite small, like the Saturn and the Ghost of Jupiter. So they're quite bright, but they're fairly small. The closest planetary nebula to us is the Helix. It's actually quite a large object. So I think it's about the size of the full moon, but it's very faint. So even though it's large, it's actually very faint. So it is a bit of a challenge in a telescope to actually see it. Same with the dumbbell. It's quite a large object, but it is reasonably faint as well. And then we have the Ring Nebula, which is a lot smaller, but it is fairly bright. Then we come to the galaxies. So we looked at Andromeda earlier. As I said, with Andromeda, it's very, very big. It spans several moon diameters across the sky. So you need a fairly low power. But unfortunately, with Andromeda from our latitude, it's very low in the sky. It never gets higher than about 20 odd degrees, I think. And as I said before, you're probably going to see the core in a telescope. The Sombrero looks something like that. If you look at, you can actually get some clusters as well. So this is the Leo triplet. You can probably get them all into an eyepiece. One nice bright one, which is always good to see because it ends up going virtually straight overhead, is NGC 253. Nice bright edge-on spiral. And Centaurus A, sometimes called the hamburger, is in a small telescope. It sort of looks a bit like a hamburger. So that's always a nice one to see in a telescope as well. And globular clusters. Now these can look really good in a telescope, especially with a large aperture. It can really resolve the individual stars if you get into like a 10-inch telescope, it actually looks something like that, and it's quite spectacular. And we're fortunate in the southern hemisphere that we've got the two best globular clusters, Omega Centauri and 47 Token A, the showcase globulars in the sky. So they're always good to have a look at if they're up. And of course, then we have open clusters as well. Now, these can be really good in a telescope because we're looking at stars. They're fairly bright. The jewel box is always a beautiful one to look at in the telescope because you get the different colours, the red supergiant in the centre. The Pleiades is another good one. They're fairly low power on that because it's quite a big cluster. And then M6 and 7, these clusters are actually embedded in the Milky Way. So you're looking at the Sagittarius star clouds as well. And then multiple stars. So stars are always good because they're nice and bright. So they're always easy to see, easy to find. And a lot of people love trying to chase down multiple stars or double stars. Everyone's seen Alpha Centauri, pair of headlights. Alberio is a lovely one. It's a lovely wide double and a beautiful contrast between a golden yellow and a blue star. And Rigel's an interesting one. It's a bit of a challenge because the primary is really bright and the secondary is quite faint and quite close. And if you can split it, it means that the seeing is pretty good. You can see the secondary star. It's interesting to note that secondary star is 100 times more luminous than the sun. Yet it looks like a little glowworm next to Rigel. Acrux is it's a 7-star system, but in a telescope you'll see two very close together and one much further away. All the other 4 stars are spectroscopic binaries within that, so they're so close that you can't split them with a telescope. Castor is another interesting one. In a telescope, it just looks like 2 stars, but in reality, this is what the Castor system looks like. Those 2 stars there are actually these 2 stars here. But each of those is a binary star as well, a spectroscopic binary. And then it's orbited by another star, which is a red dwarf, and it's also a binary. It's a red dwarf binary. So this is a 6-star system. So when you look at these multiple stars, the stars you see aren't necessarily all the stars in the system. Okay, nice and short and sweet tonight. Any questions?
Yeah, telescope sizes.
Aperture, you mean?
Aperture, yeah. Where would you start and then go up to?
Yes, well, it's
if cost wasn't
cost is a big thing, yeah, and it depends on the type of telescope. Well, like if you're going for a refractor, about the biggest refractor you can get is about a 6-inch, effectively. But they give you probably the best views. A good refractor is probably about the best telescope you can get. But if you want aperture, probably a Newtonian or a Dobsonian, you can get, that's probably gives you the biggest bang for your buck. Because you can get like a 12-inch, which is still reasonably portable, and still give you very good views and pulls in lots of light, and you can see you have very faint objects. So yeah, the budget is the big thing, really, I guess, and also portability, because there are a lot of people I know that they bought a 12-inch Schmidt-Cassegrain, and they find they just can't handle it. It's just too hard to move. It's so heavy. Yeah. So that's another consideration. And then some of these, some members have got like 18-inch Dobsonians, so they need a trailer to transport them, and then it takes them an hour to assemble it at the viewing site. So yeah, there's lots of considerations. I hope that answers your question. Any other questions? All right, well, thank you very much. And I'll be back in about half an hour or so to do the main presentation. Thank you.